All right, so we're going to jump back into section 13.4 where we're talking about surface area of three-dimensional shapes. We've gone through quite a few of them at this point. We looked at prisms. We looked at cylinders. And we looked at pyramids. And our next example is cones. So on a cone, again, the lateral area would be, so if you imagine like a cone at Brahms, you're going to have to imagine a sugar cone. That's the small one that looks like a waffle, okay, but it's actually called a sugar cone. So imagine that one is a really good picture to have in mind, simply because it's flat. Waffle cones have these indentations along the edges that are not quite cone shaped. And so the cone part itself would be the surface area, right? The part you eat. The flat part on the top or the bottom, so in that case the circle, if you see in my picture on the screen, that circle shape right there is going to be your base. So this right here is your base, and then the part that is the waffle of the waffle cone part, right? The actual piece is going to be your lateral area. And the area itself is always lateral area plus the surface area. The base area. The lateral area here is based on the length of the side of the cone. Again, it's the slanted length. So this is actually pi RL. It's based both on the radius of the circle and upon the length of the side. So here's your length of your side. Sorry, that's not what I meant to click on. Here's your length of your side, and then here's your radius of the circle below. And then the area of the base, well, the base is simply a circle, and we know that the area of a circle is pi r squared. All right, any questions on that? I don't have a specific example. These are nicer to put in usually because they usually give you the L. Like they did on this problem over here. This one actually gave it to you as well. Instead of just giving you the height of the building, it gave you the slant height as well of a side. So these tend to give you those pieces of information, and they're more directly applicable to be able to be used. All right, let's look at a couple more. We have spheres. So spheres don't have any lateral area. They just don't. So it's all one shape. It's the shape of the ball that's on the outside of it, of course. So a little bit of vocabulary first before we get to the actual surface area formula. A great circle is actually the circle that would cut the sphere in half. So if you imagine like on the Earth, this would be, right, the equator line would be a great circle if you sort of could cut the Earth in half along the equator. The circle is, the radius is the same as the radius of the sphere. You can think of the intersection of the sphere and a plane through the center of the sphere. If you're thinking about the Earth, the center of the Earth, the center of a ball, whatever image it is you have in mind. A sphere has infinitely many congruent great circles. There is that latitude circle, that through the equator one that you sort of see imagery here. But if you think about the lines of longitude on a globe, you can think about infinitely many of them. So if you imagine them going, and that's not all of them either, but if you imagine going through the North Pole and the South Pole with a great circle, right? The line of longitude would be through this longitude line, and then we could slide it around just a little bit this way, and we could go a little bit this way, and we have infinitely many of them. And that's not the only way you can do it. As long as you have two antipodal points on the circle, on the sphere, this will happen. It's just that the North Pole and the South Pole are easy for us to sort of think about as being antipodal, right? They're on opposite poles. The surface area for a sphere is actually 4 pi r squared. And we're going to do an example that actually combines this sphere with the cone one that I did before, that I talked about before, and thinking about how we would go about combining those objects together. So any questions before I move on to the example that's used? Okay, so we're going to do an example of an ice cream cone. We're going to do the surface area of the ice cream cone itself, which is not quite a sphere, and it's not quite a cone because we've joined two objects together. So if you imagine the surface area, again, is always the area that's on the outside of the shape. So let's talk about the sphere itself first. What do you notice that I'm going to have to do to my sphere formula to find the part that applies to the upper part of this cone? Yeah, we're going to have to divide it by 2. I only have a hemisphere, right? It's just half of the sphere that's sitting on top. So as I'm thinking about this one's surface area, I'm going to start with the hemisphere on top. And on bottom, I have only the lateral area of the cone. Does that make sense to everyone? I don't have the top of the cone because it's sort of inside of the object now instead of being on the outside of the object. So just like Kenzie mentioned, the hemisphere I would divide by 2. So the lateral area, or the hemisphere, the sphere surface area, is 4 pi r squared. So a hemisphere would be dividing that by 2. And then if you'll remember over here, the lateral area portion of my cone was this part at the beginning, the pi RL part. So this is plus pi RL. I'm putting the wrong screen. Oh my word. I need to undo that. Sorry, I put it in the wrong screen. Flipping too quickly. There we go. Plus the pi RL part of my cone. Okay, so for starters, to everybody understand where all the pieces came from in the formula that I have not yet evaluated. Okay, this one wants us to find the surface area of the ice cream cone. Assume that we have a right circular cone topped by a hemisphere, and we have an image where it gives us a couple of pieces of information, but not everything that we need. In particular, it gives me what? What can you tell me in this that it gives me in terms of this equation? It gives me the radius. What's my radius? 4. So I have 4 pi, my radius is 4, so 4 squared. I'm actually not going to write this as 4 anymore. This 4 reduces, so let's just take care of that. This 4 and this 2 reduce to a 2. So I have 2 pi and then 4 squared. I have plus pi times the same 4, but I don't have L. It's not given on this one. Why is L not 8? Yeah, 8 is the altitude, right? It's the straight up and down distance, and L should be a slant distance on the side. So my L is actually supposed to be this piece over here. Right? How am I going to figure out what that piece is? You bet. It is the Pythagorean theorem. Nicely done. So let me draw out this triangle that's embedded here so that we can put the Pythagorean theorem to use. It tells us that my height or my altitude here is actually 8, and that my radius, which is the side of this triangle, is 4. So call this whatever letter you like. We'll just call it L. I mean, we don't have it used as anything yet, so L will be fine. And then thinking about this object, I have 4 squared plus 8 squared equals L squared. So what's 4 squared? And 8 squared? 64. Okay, so what's 64 plus 16? 80. And I would take a square root. Now, in general, this value would simplify, but I don't really need it to because that's not the question I'm using, right? I'm just using this piece of information inside of another formula, so it's perfectly fine to leave it a square root of 80. Okay? Again, these are application problems. It doesn't make sense to leave things in terms of radicals or pies, so we're going to use our calculator to simplify all of that anyway with 2 decimals. So as we're working through the process, if you want to be a little bit more careful, keep 3 or 4 decimals until the very end and then round off to 2. That's a good idea. So I have 2 pi times 4 squared, or 16. And this first piece is actually 100.53, and it's 0.96, and so that'd be 10. And then I have pi times 4 times the square root of 80. And that's 112.3970. So if I add these together, I will get, and round to two decimal places, I will get 212.93. What are my units? Close. Centimeters squared. Anytime we're working with area, and surface area is certainly area, we will have square units, so centimeters squared. Do be careful inside of a problem too. Occasionally they will give you units where they don't match, right? So they might give you meters on one unit and centimeters on the other unit. So if that were to happen, you need to switch one of them into the other one. So turn it all into centimeters or all into meters before you proceed. So don't mix up the units inside of a problem. Do be careful that they all match.